Good afternoon, everybody. Thank you very much for joining us today. My name is Ben Parker. I am the sales manager at Quantum Design UK and Ireland, and I have the pleasure of joining you today with my colleague Stefan Kaiser from InfraTec. And we would like to give you a short presentation webinar based around their infrared cameras for thermography, and more specifically their proprietary high dynamic range, or HDR option, which is useful for measuring the temperature of scenes with objects of very different temperatures. So first of all, thanks everyone for joining us. I do hope everyone is managing to stay safe and well in these rather challenging times. I'd like to thank Stefan and also Emily and Angela at QD for helping to organize this webinar. So just a little bit of housekeeping. We factored in for about a 45-minute session. So the structure of the webinar will be as follows. I will kick things off with a very short introduction to quantum design for those people who are not aware of us. And then my colleague Stefan Kaiser from InfraTec will take the reins and get down to the nitty-gritty of the present challenges and solutions for high dynamic range thermography. And then hopefully at the end of those two talks, we will have some time left to field some of your questions. So for asking questions, how I would like to do this, please, is that if you have a question, please write it in the question panel, which everyone should have access to. And then at the end, I will go through the list of questions sequentially, and myself and Stefan will answer those during the end of the webinar. Okay, so if there's any interruptions, please bear with us. This is as new for us as it is for many of you. So if we do run into a technical hitch, we will attempt to restart the webinar. If for whatever reason we cannot restart the webinar, we will then send out a recording of that a little bit later on. Okay, so just to give everyone an introduction to quantum design first of all. So hopefully everyone can see my my presentation here. So who are quantum design? So quantum design are located in Leatherhead, down in Surrey, which is just southwest of London. We are a fairly small team of 8 people in sales and marketing and service, and we are part of the worldwide quantum design group, which is a much larger organization. We have a presence in 20 European countries, and multiple offices throughout Asia and North America. We have roughly 500 people worldwide, and our ultimate parent company is Quantum Design International, which is based in San Diego in the United States. Now we are a hybrid manufacturer and distributor, and this what came about from the merger of two companies, the first being Quantum Design, who are an American manufacturer of low temperature instruments for the measurement of magnetic and physical properties, and that of LOT or LOT Oriel, which may be familiar to some of you, who were and continue to be a well-established distributor of scientific instrumentation in Europe. So we're a very stable company. We have been in business for 35 plus years, and we have many long-serving, experienced and knowledgeable staff. So our global structure, as I mentioned, we are part of Quantum Design International, which is comprised of a presence in Europe, Quantum Design Europe, and then offices in Asia, including China, Japan, and also a presence in India and North and South America. Then in Europe, this is some of the territories that we cover. So myself, I'm sitting in Leatherhead in the UK, but perhaps some of you are from other European territories. So we also have offices in France and Spain and Italy and Germany, and some support for the remaining territories in Europe. And again, to say again about our presence worldwide is not just in Europe, but on every continent. Okay, so I mentioned we're a hybrid company in the sense that we have both a manufacturing and a distribution channel. So in terms of the products that we manufacture, these are primarily based for measurement of fundamental properties of material at low temperature or in a high magnetic field. So our two flagship products are the MPMS, which is a squid-based vibrating sample magnetometer, and the PPMS, which is more geared up for measurement of bulk properties of material, such as heat capacity or electron or thermal transport or other optical or magnetic properties. We also have some more universal products that we manufacture in San Diego. Two of the newest ones being a range of helium liquefiers, or more suitably reliquefiers for recycling of helium gas and liquid. And our newest product is the optical, which is an ultra low vibration 1.7 Kelvin 7 Tesla magneto-optic cryostat, which is designed for microscopy experiments. Then we come on to our distribution products, which was born out of the LOT or the LOT Oriel side of the business, and this is quite broad and eclectic, as you can see. So this covers many different products, from some other mechanics to imaging, so a range of cameras from X-ray into the infrared and even hyperspectral. Some fairly niche products like spectroscopic ellipsometers, and also some other products in some complementary areas in electron and X-ray microscopy. So just a brief overview of who we work with in the UK and Ireland in terms of our suppliers. Some of these may be names that are familiar to you already, but the one I've got starred there, as you can see, that we would like to talk about today is a company called InfraTec, who are a manufacturer of infrared cameras and thermography solutions based in Dresden in Germany. Okay, and then I'd just like to finish up by telling you a little bit about how you can contact Quantum Design, especially now in the current situation. This is somewhat different to how it would be before. What we are now offering as our kind of first port of call is a video conferencing setup, whether that be with our sales or our service personnel. This is sort of facilitated through the Microsoft Teams platform. Now, you don't need to have Microsoft Teams installed on your PC for us to send you an invitation. You merely have to have some audio and a webcam if you wish. So please, if you have any further questions after the webinar, or you would like a dedicated one-to-one follow-up with one of our sales engineers, then please let us know and we can arrange this for you. And please stay in contact. This is the best way to contact us and to keep up to date with our new products and the news and so forth. So we have our website. We can see the web address at the top there. Please also follow us on LinkedIn and Twitter. And if you really want the most relevant information, then please contact us to subscribe to our quarterly newsletter. This really gives you the most detailed information straight into your inbox once a quarter. Okay, so that's all I'd like to say on quantum design. So what I would like to do now is to introduce my colleague Stefan Kaiser from InfraTec, and he will then talk to you about high dynamic range thermography and the challenges and solutions to this. Thank you.
So, okay, everyone. So my name is Stefan Kaiser. As Ben already announced, I'm a sales engineer of InfraTec. So what I want to show you today is a little bit of InfraTec about our technology called HDR, and also to give you some examples what is really possible with this kind of technology. And before I will do this, I want to teaser this little webinar by the first example. So next slide should be this kind of a light bulb. And what you will see next is this light bulb will go on and off, which covers normally a wide range, a wide temperature range. And you will see that this whole scenery can be captured with our HDR technology. And hopefully by the end of this webinar, you will understand why this is so beneficial, why we can keep low temperatures and high temperatures in the same image with a good resolution. And without further ado, I hope that this video quality is streamed to you well. And then you have seen this going on, going off, temperature rises quickly, temperature goes down really quickly again. So this is the teaser for this kind of webinar for the next minute. But before I go into the technical details, let me introduce a little bit InfraTec, who we are and what we are doing. So InfraTec is a company exclusively dealing with IR technology. InfraTec was founded in 1991 here in Dresden in Germany, and we are still a founder-owned business of approximately 230 employees right now. And there are two business units currently. One business unit is dealing with infrared sensors. That means electronic parts that will be built in third-party devices. But on the other hand, we are also facing on the infrared measurement division. That means we are dealing with infrared thermography, infrared imaging, and that's the business unit I'm from. So we are really focusing on camera equipment, starting from handheld cameras, going to handheld cameras, stationary cameras, but our main focus is to address the scientific market with our cooled cameras from the Image IR series. So we are not only providing hardware of infrared technology, but we are developing these ourselves, but also combining hardware with the necessary software suites to provide a really good user experience, but also which is what I think is really necessary to provide training, transfer knowledge into the market, to have a really nice roundup. And to do this, we are focusing on the high-end segments of the market. This is just an example of two products here, and what you see here are cameras providing a high resolution in first place. This is a side of our approach to the high-end market, but also these cameras provide high accuracy and high thermal resolution, but also, as I said, software is a big part of the business, how to deal with the data, how to acquire the data, how to analyze them. And that's why we develop our own software suites also in-house to provide a good set of analyzing tools, Windows-based software, but also supporting your development with an SDK, with a MATLAB implementation, for instance. And yeah, the main focus of this presentation is the high-end spectrum, the HDR, and therefore I want to continue with a rough introduction our Image IR series, because the feature is directly connected with this camera series. And may you are familiar with this kind of technology, these so-called cooled cameras. And what we try with our products is a very modular approach. That means the devices are built on customer demands. There are many features we can combine to build up the perfect measurement device for you, for your application. This includes filter wheels, motorized focus, for instance. All our housings are kind of robust metal housings with a high IP rating. We provide the highest resolution you can get on the market, but also high-speed detectors. And of course, there are other unique features like a load jitter for the triggers, which are necessary, good interfacings with state-of-the-art technology. To give you a little bit of an introduction, these products are built of three main modules. The module 1 carrying all the necessary hardware for handling the lens, handling so-called filter wheels. This is a part of the HDR2. We come to this later, but also the individual module 2 carrying the sensor and the electronics. But then you have the module 3 with all the interfacing, with the data interface, with the triggering. And this again is a modular system, can be built out of different parts, user specific. And yeah, as the filter wheels are relevant to understand how HDR works, some words to them at the beginning. So in our cameras, we can build up to 2 such wheels with 5 positions. And these filter wheels are, of course, remote controlled and can be equipped with either ND filters or spectral filters. And by combining 2 of these wheels with 5 positions, of course, by the math, we have 25 combinations available to adapt also the spectrum and the temperature range to your application. The next is just an overview of the main products in the lineup. So the Image IR series comes from Image IR 5300, which is a really high-speed detector. then going to the more or less the working horse, the 8300, which is a very flexible device, but also carrying a lot of speed. There are also long wave detectors available, but the beauty of our product line is really the 9400, 9500, and 10300. These are really high resolution cameras that can be combined with also a technology called microscan for boosting the resolution. But today I will not talk about resolution, but I will talk about HDR, which means broad temperature ranges. And to begin with, I think this is just these fundamentals. So you nailed down your application, you know that you want to do a contactless temperature measurement, and you know that you use an IR camera to convert this radiation coming from the object into some kind of digital information, and then these information go into a PC in some kind of software to be transformed into temperature information. And this is your goal, and this is more or less the measurement process you do. But also fundamental is the kind of sensor technology we use. There the name cooled cameras came from. So we are talking about so-called photon detectors. These are detectors directly converting the IR radiation into an electrical signal. They are really fast snapshot detectors, but on the other side, these detectors need to be cooled. Nowadays, this is done by Stirling engines, Stirling coolers. So that means you have some moving parts in the camera, make these things a little bit more bulky and also complex. But the beauty of it is really providing a good thermal resolution, but also time constants in the microsecond range, but also the acquisition mode is snapshot. That means all the pixels will be read out at the same time. And these properties of the detector are necessary then to perform an HDR measurement. And why this is so, we have to speak a little bit about the principal acquisition of such a detector. You know this a little bit, but I mention this because it's necessary to understand. So these detectors collect the IR radiation. Yeah, you can think about this like an electric capacitor, and there is a nonlinear transformant function between this radiation and the fill of this capacity. And what you want to do is adapt the time, how long you catch up or you collect information. But this needs to be in a balanced way. So if you have a poor amount of radiation, for instance, and you do not collect long enough, then you're so in an undersaturation, for instance. So you collect this amount only by 1 second or one period of time, and you're not in the linear state of this nonlinear function, and that's why you have not a controlled behavior of the detector, and that's why you cannot use your the information from the detector properly. On the other hand, if you have a lot of radiation, for instance, and you collect the same time, then you may overshoot the whole process. Your saturated situation of the detector, and again, you're leaving the sweet spot of the detector, the linear fashion, and then you again cannot use the information from the detector any longer. So you need to balance the time you're collecting the data, and this is a matter of the amount of radiation coming in, matter of your sensor sensitivity. So this is really a challenge also from the technology, from the user experience to balance these things out. So this leads then to the challenge of balancing the integration time with the incoming radiation amount to have a good quality image, a good thermal sensitivity. And here in these two examples on the left, you see a fairly long integration time for optimal thermal contrast of lower temperatures. So you see here at the hand, you have a good thermal contrast, but on the other side, at the tip of the soldering tool, you see you have already reached saturation. On the other hand, if you fine-tune the integration time differently, you see here that the tip of the soldering tool now has a good thermal resolution, but contrary to this, you see at the portion of the hand is no longer visualized nicely. So the problem is that you get so-called sub-ranges. So one specific integration time is only covering a certain temperature range. So, and the problem is what you do when you use really short integration times. For instance, if you want to cover a lot of radiation, you use a short integration time to not oversaturate the detector. But on the same end, if you reach the limit, you cannot set the integration time shorter. What you do, or what we do in our cameras, you install ND filters to reduce the intensity coming to the detector, and then you can again use a little bit longer integration time, go in the sweet spot of the detector again, and then measuring a higher temperature range overall. Technology-wise, this is realized by implementing these ND filters in these wheels you've seen earlier, and by combination of these filters, we adapt to different temperature ranges. So to sum up, you will have something like this in your final camera. So we have here temperature range, for instance, on the x-axis, and on the y-axis you see different ranges and sub-ranges. So the orange part are different sub-ranges with non-ND filter. If you want to measure above, you have to apply the first ND filter, which is the blue range. This range goes then, in this case, up to 600 degrees. But to achieve optimal thermal contrast and measurement accuracy, this range is then also divided into two sub-ranges. And this goes again and again if you reach your top level. But the thing is that you do not want to be limited to these sub-ranges. Actually, you want to have broad temperature ranges to cover heating processes, for instance, cover electronic boards which defects into the 100 degrees Celsius, something like this. And the state-of-the-art technology is the so-called, or we call it multi-integration time. That means that you combine ranges of one filter position. So for instance, we combine these four sub-ranges here with a no ND filter, and fastly change the integration time of the detector, merge the images together, and what we get is an image like this. So you see here that the soldering tool is displayed with a good thermal resolution, but also the lower portions on the hand, the lower temperatures are also resolved nicely. And this is done by the MIT technology, and this is also this is the bottom line of HDR also. And then you can ask the questions: what happens when I want to change temperature range or change the filter position to get to higher temperatures? Then of course this change here needs time, because you need to rotate these filter wheels. But also for quick changing processes with high dynamics in the image, these wheels are kind of slow. So it's not possible for ordinary IR cameras to cover a high dynamics in one image. So you have to do a compromise. Which temperature range you want to measure? Do you want to focus on a high temperature range in your experiments or in your image, or you want to focus on the low end? So this is a kind of compromise until now. And the simple question was, why not making this change of the filter quicker? This may sounds like an easy question, but the technical realization is really a piece of engineering. So basically, that's what we did. We made these wheels faster, and by having a fast rotating wheel, you can imagine that these filter positions change really quickly. So I show you how this looks actually in a movie. So this is such a filter wheel, and then it will speed up and rotate with approximately 5,000 RPM. And by seeing this image, you clearly understand that it's needed to synchronize really the detector with this kind of wheel, and also to go back to the MIT algorithm, use these algorithms then to acquire the data correctly. And by doing this, synchronizing these fast rotating filter wheels in the right way, then we can capture temperature ranges of 1,500 Kelvin in one image with one shot. And currently, we have this technology available for our model 8300, but other models are approaching. So what we're doing with the HDR, we combine so-called HDR ranges of different filter positions to one image. So like you have seen in the first example, this light bomb goes from almost room temperature to 1,200 degrees in one image. In one video, we were able to cover this whole temperature range. And by giving you other examples, I want to show you here. This is an image of a fuse right before the fuse blows. And what you can see here in one image is a broad temperature range of 42 degrees to 500 degrees approximately. But I also can show you this as a video to underline the performance of this HDR. And you see here how the fuse gets hotter and hotter and reaching the limits of the normal filter positions. This is normally not possible with an ordinary camera, but with our HDR feature, we are able to collect these kind of images. So next example, maybe this is also related to a nice software feature of ours. So what we have here, we have simple experiment, a kind of candle, providing also a very high temperature. And the flame or at the hotspot of this object. But in the same image, we have also here a hand of a colleague of mine who did this, who made this picture. But to show this really on a screen with a nice resolution, we have here in this rectangle. Here in this rectangle, we have our so-called temperature loop function. So that means that the whole image corresponds to this palette here, to this scale, but this section here corresponds to a very tiny scale here, and then you can resolve in one image maybe this portion here with the high temperature, very nice, but on the same time here you can resolve the hand or the fingertip, very nice. So this is again a combination of an HDR image, but also a combination of our temperature loop function. Switching back to this example you have seen at the beginning. So I will replay this, and now you understand why it's so beautiful to have to see here the light bomb itself, so the glass covering a low temperature, but also to see here this filament, so the actual element producing the light, but also producing a lot of heat. It's a kind of old-fashioned technology, but it's nice to demonstrate. You see how quickly this process changes, really the dynamics behind it, and we are able to capturing all of these. And as a last example, I will show you maybe a little bit of an outview of HDR technology, which is possible, and to combine HDR with spectral thermography. So remember, we are able to have two wheels in our cameras. That means one wheel we can have an HDR wheel, which is fast rotating, but the other wheel will stand relatively, will stand constant in a fixed position and can be changed independently. So we are able to combine an HDR, a high dynamic image, with spectral thermography. So coming maybe to the spectrum of glass, you can imagine changing the sensitive wavelength of your camera to, for instance, this section here where the emissivity of glass is very good. Then you measuring the glass surface of this kind of light bulb without distortion. But on the other hand, if we switch by installing a special spectral filter more to this spectral range around 3 micrometers, then we benefit from the transparency of the glass and looking through the glass on the filament, being not disturbed by the glass surface again. And this is a really unique feature of ours, to have two wheels in one camera, to really do some kind of experiments. And it's easy to understand that you can change between these modes instantly. So you do not need to deassemble the camera, changing everything. So we will equip the camera with the necessary filters. The HDR is built in, which is also able to be turned on and turned off. So there are many possibilities of using this technology, and I'm really excited to hear your feedback, your ideas of fitting applications, and then talking with you through the technical aspects, finding the right solution for you. And with this, I want to sum up my presentation. So we have learned that standard IR systems have limited temperature ranges defined mainly by the filter position. We know that standard filter wheels are turning relatively slow, so they are not capable of covering footage with a high dynamics. But also our HDR technology is able of doing exactly this, covering a broad temperature range up to 1500 Kelvin in one image. The current available model is the Image IR 8300. And we also learned that HDR can be combined with other features, can be combined, for instance, also with motorized focus. So we provide really flexible solutions. And by this, I want to thank you for your attention. Again, I am excited to hear your feedback, to get in contact with you, but also Ben would welcome to join these conversations. So maybe Ben, you get back to the presenter role.
Yeah, thanks very much, Stefan. That's an excellent presentation. I can see that haven't had any questions raised thus far, but I think we're running pretty much to time, so we do have a little bit of time to answer any questions that anyone might have. So perhaps I'll give it just a few minutes. If you have a question, please write it in the question window, and myself and Stefan will endeavour to answer it for you now. Okay, excellent. So first question, okay, nice general one. What are the applications for HDR? So Stefan, I don't know if you want to take that one.
Yeah, so basically each application covering a broad temperature range. So for instance, we had requests from companies building engines, more or less rocket engines, for instance, and these engines are on the test rigs, and they want to test the whole lifetime circle of these engines. So these experiments cover a lot of dynamics of temperature ranges, and this is an application able also electronics, I guess. There you can have a lot of temperature ranges. Materials testing can be an applications, general one. So basically everything correlated with fast high dynamics in your images. These are good examples for HDR usage.
Yeah, and maybe I'll just add to that, Stefan, as well, is that what we're really talking about is not just a temperature rise, but also a cooling or a quenching of something. So if you have something that starts at a high temperature, and then you want to image the cooling process or the quenching process, which might be over a few hundred degrees, and might happen relatively quickly, then of course the same applies from going from hot to cold than it does from cold to hot. Okay, next question is the integration time changed when using a HDR technology, or are the filters the only elements that are changing?
So may I go back to this slide? Hopefully everyone can see this. So what I explained is that we have done specific HDR ranges, and between these ranges we change the filter position. This is absolutely correct, but also this range and this range and this range can have a different integration time. So we're doing both. We change integration time and also change filter position. Exactly, we capturing the image in the right moment when the right filter is in front of the detector. So, and this is a kind of continuous operation, of course, to capturing these kind of examples I showed you.
Okay, and I think the next one we've got is essentially the question is, can HDR be used on a long wave and a mid wave camera?
So currently we have the HDR ready on the Image IR 8300, which is a mid-wave camera, approximately from 2 to 5.5 micrometers sensitivity. But we're working on bringing the HDR to a long wave camera too. So that means, of course, you have two separate cameras, but you can have the technology on both these devices. So, but the HDR for the long wave is still in development. So we are optimistic to launch this in the next months. But as always, development is a kind of a technology process. So we figure this out in the next time frame.
Yeah. Okay. Thanks, Stefan. I think there's a question about the cost of the cameras, so that's something which can be addressed offline, mainly because I think we have attendees from different territories here, so pricing may not be always applicable. So I've made a note of that request, and we will get back to you offline about that. What particular application, Stefan, for your information is bushfires or wildfire. This relates to. the first question. Next question then is, does the camera form the full image of combined ND images in the software, or is it done electronically in the camera?
So current state,
and specifically, how much RAM does this then put a? Does this then mean you have to have a minimum spec in terms of RAM for the PC, etc.?
Yeah. So currently we are transferring all the data to the PC, to the software. So the answer is that the algorithms are, or the calculations are done in the PC, and commonly our packages that we deliver to our clients include a fitting PC and with all the software installed, so ready to run system. So these are state-of-the-art PC systems. For this kind of camera, I recommend an i7 processor and an SSD. So of course we will support if you want to switch the PC to your own one or whatever. But again, the data is transferred to the software that does the calculation. Yeah. So, and by securing this, we are using state-of-the-art interfaces so that we can achieve that there's no frame loss. So for this kind of camera, we're using a 10 gig E optical fiber connection, which provides a really robust bandwidth of 10 gig E, 10 gigabit per second, but also is capable of covering a lot of distance, so it's no big problem to have your camera stand far away from your control or acquisition PC, for instance, in R&D and labs. If you're not, if you cannot be close to your camera, there's no big deal to cover long distances with this technology. And also, what I mentioned, cameras can be equipped with a motorized focus, which gives you a full control about all the features of the camera. So it's really not necessary to be near the camera to run these kind of operations. You can, as I said, switch on and switch off the HDR by software, and that's why 100% remote control is easy to achieve.
Okay, great.
Okay,
thanks, Stefan.
Hopefully this covers everything.
So let me have a look. Yeah, that is the last question that I have that I can see here. So last chance then, I think, for anyone if there's any more questions. I'll give you maybe one more minute for any further questions, and then if not, we'll wrap up.
Okay. Or maybe I show this video again. Not so sure if it's showing. Yeah, it was shows. Yeah.
Okay, great. So I think we'll leave that there. So if you have any further questions, please don't hesitate to get in touch. You can find our contact details on our website, which is www.qd-uki.co.uk, and as Stefan shows there, Stefan and myself's direct email address should you wish to contact us and have a follow-up conversation. So great, thank you very much to Stefan, thanks to Emily and Angela, and most of all, thank you to everyone out there that have bared with us and spent an hour of your time with us. I hopefully you found it useful, and please look out for the next series of webinars from Quantum Design. We are not just thermography, so please follow our Twitter and LinkedIn pages to be updated with the next series of scientific instrumentation webinars. Okay, thanks again.
Yeah, thanks also from my side, and then bye-bye.